So here's another crazy design. This is called a lat square. We've talked about procedures for dealing with a nuisance variable, right? Blocking. Right, so you get heterogeneity of external units, you get people that are the same on some variable. What was it? Experience, knowing a second language to test second language learning ability was a nuisance variable, and we blocked on that, and that would work pretty well. You can certainly use repeated measures, which are obviously a special case of blocking, because you're using the subject as their own control. So those are a couple of ways to deal with nuisance variables. One nuisance variable. You can also do something which we're not going to talk about in this course, called ANOVA, which is analysis of covariance. What this does is it statistically controls for a nuisance variable. So let's say you thought that we did some study and we thought that, I don't know, your GPA, like how you do in school, would affect how you scored on something besides the treatments. We can actually measure your GPA, and we can statistically remove the variance due to GPA. It's not ideal, but it's doable. It's actually pretty simple, and if you look at SPSS in the general linear model procedure, there's a thing at the bottom that says ANOVA, and then it'll say covariant. You can just put a variable in there. So if you want to play with it, you can. The thing is, it's just not an ideal way to do things. It's better if we can make sure that this nuisance variable subjects are the same on them, like we do with blocking, because then we know they are, rather than saying we're going to use math to do it. So what if you had two nuisance variables? So now you have a third variable you're interested in, but you have two nuisance variables. That can happen. Sure. It's rare, but it happens. So now we're going to basically sort of put together two randomized block designs into one special, exciting, and annoying kind of analysis of variance. We're going to put one nuisance variable in rows, like we would usually, and one in columns. And I'm much more excited about that than I should be. It's getting near the end of the term, and I'm really excited about that motivating. Also, there's still lots of stuff.
But the sun is shining.
The sun is shining. It's very nice out. It is true. It's a very nice day. It's very pleasant. Soon the snow will melt. I will ride my bicycle again. Almost certainly illegally, because I probably shouldn't be riding a vehicle on the road. Okay. In fact, when I was 5, a woman from the Canadian National Institute for the Blind came by, the social worker, to enroll me, And they said, well, I'd like to meet your son. Where is he? My dad goes, there he goes. Doesn't play. She said, you can't ride a bike. And my dad said, look, there he goes. So you get something that looks like this. That's, again, I'm starting to just entertain myself both with transitions and fade-ins and stuff. So these columns and rows are actually, these are different levels of a nuisance variable. And this is where it's weird, and I'm sorry about this. This is not my convention. I wouldn't do it this way, but this is what you see in textbooks and stuff. So that's why it's like this. A, B, C, and D aren't different variables. They're different levels of the one independent variable we care about. Okay? Put that over there. So these are levels of a factor of an independent variable. They're not different independent variables. So each level occurs in each ordinal position. Okay? So each row, in other words, each row and each column has each level once. See, now you might say to yourself, well, why don't we just do this where we measure those two nuisance variables, and then we do in this case a 4 by 4 by 4. Well, suddenly this becomes a much bigger design. So instead of needing 16 people, I need 64 people. Is that right? Yeah, 64. And that may not be ridiculous. 64 people isn't impossible. When it becomes a 5 by 5 by 5, it gets ridiculous. I've once had a student use this, and she did an 8 by 8. Okay, so it was 8 levels of each nuisance variable and 8 levels of the independent variable. So she did what? Just an 8 by 8. That's not so bad, right? That's what, 64. What's 64 times 8? A lot more. We didn't have that many undergraduates to study. And she'd still be collecting data. And she did a great thesis, but it was like we needed to do it this way. It was cool. It was about detecting poisonous odors in humans. It was very cool. So each row, each column. So look, if you had a 2 by 2, well, you know, if you had a 2 by 2, you wouldn't do this. You'd go a 2 by 2 by 2. That's easy. Or if you had a 3 levels, when you start to get 4, it starts to get a little unwieldy. Think about maybe using one of these Latin squares. So you need an equal number of rows, columns, and independent variable levels. And the model, which we've kind of been avoiding thinking about the models last week or so, but in this case, it's any score equals the grand mean plus the rows, the columns, and the independent variable. And then what's left over. X equals mu plus alpha, beta, gamma, epsilon. Okay? Alpha plus beta plus gamma plus epsilon. One of the things you'll probably note here is that there's no interaction here. Even though we have 3 variables, there's no AB, no AC, no ABC, no BC. Because every level hasn't occurred with every other level, we can't test interactions. Okay? So the analysis of variance looks like this. Rows, columns, independent variable, residual. P is the number of rows, number of columns, number of levels of the independent variable. So you have P minus 1 for rows, P minus 1 for columns, P minus 1 for independent variable, and the residual. You test mean squared for individual, for the independent variable by the mean squared for residual. Okay. Good?
Residual is now
What's left over?
error.
Yeah, it's error. It's what's left over. See, but it's not really individual variation.
Yeah.
It's individual variation within a row, column, and treatment level. So we call it residual. It's just shorter. P is the number of rows, number of columns, number of rows, because everything has to be. There are weird designs you can do where you could have a limited subjects one, but you have to have just 2 subjects in each of those cells or more. You can't just have one because you couldn't do variance calculation with 1. Yeah, please. Oh, no, I thought you had your pencil up with you right there. Don't ever go to an auction, you end up buying something. Sold to the woman in the front row. It'll be $27,000. Unlike hierarchical designs we just talked about, this is actually useful. Now, you've got to meet a pretty stringent set of assumptions, but if you can, there's nothing wrong with this design. So conclusions about this. So like I said, the assumptions are stringent. The big assumptions here are same number of rows, columns, and independent variable levels, and no interactions. And you can't tell if there are interactions. Like that's not something you can find out from this.
Wait, what are the rows again?
Well, same number of rows, columns, and levels of the independent variable. That's probably doable. And no interactions. That's the hard part because there's no way to know if there's no interactions. Because to find out if there's interaction in a 5 by 5 Latin square, you actually need a 5 by 5 by 5 design. Well, you need to have every level occur with every other level of every level.
Oh, yeah.
Yeah, and to define this interaction by definition, right? But you can't do that with this. It's impossible. Or, as Ralph Wisdom would say, it's impossible. You fail statistics? That's impossible. P is less than 0.05. That's not even remotely funny. I don't know why the final point doesn't keep showing up here. So yeah, the final point is just the equal number of rows, columns, and levels of the independent variable. There's nothing wrong with these designs. Unlike the hierarchical thing, which is garbage. These are really okay. Now, what could you do? There's other things you can do. I remember we had when I was in grad school, we had a test. Was it our final? Probably our final. We were given a partial Latin square, a 5 by 4, and asked, how do you analyze this? And I can't remember how I figured that. I figured that. Or you could do something really cool. You could have 2 different Latin squares. And then you would have, so you have 5, let's say a 5 by 5 and a 5 by 5, but the positions are different for each. And then you have a final, so you have rows, columns, independent variable, residual, and what other source of variation would you have? Is it? Which?
The order.
The order's taken, yeah, the order you can't actually deal with. The design's in the order. Between squares would be the method. You can also do something really weird, which is called a hyperlatin square, which is actually a cube. So it's like that. And the levels of the third variable, you don't use letters, you use Hebrew letters, and I don't know why. So don't worry, you never run into that. That's the kind of thing you're going to be reading in an advanced stats book. You get to the final thing of the chapter on Latin squares, and you go, yeah, well, I'm never going to do this. And you just, okay. So there's a lot of interesting things one can do. But for our purposes, the Latin square is a perfectly fine design and not something you should avoid, if necessary. But it's, like I said, I've had, God, I think I figured out the other day in my career, I think I've supervised almost 100 honors thesis projects. And I've had one person do Latin square. But it was totally useful. Like, it was a completely reasonable design. It was that design. All right, questions?
Okay, so what if you're given data that already has an interaction taken care of? Like they give you the value for the interaction?
I don't understand what you mean.
Okay, so the one that I showed you yesterday, where they had
Right.
already accounted for the 2 levels in each value.
Yes.
So then, because I'm not looking at an interaction anymore, could I use this to look at
No,
those?
because
Why?
this is making a very, well, what you could do in that case, if there's an interaction that you know is not significant.
Yeah.
Interesting question. There are cases where I can't find chalk. Okay, wait.
You threw it on the ground.
So there are, let's just say, you have a straight ahead 2 by 2. Okay? And we know typically our model for a 2 by 2 is this: x equals mu plus alpha plus, beta, plus alpha beta plus epsilon. It would be nice, possibly, to simplify this and remove that term. Right? So let's say you're sure there's no interaction. Let's say you look at the and it looks like that. Well, not like that's no good. So it looks like this. Just exploratory data analysis, you look and you see you got parallel lines, but you're having trouble finding significance. Well, maybe get some more degrees of freedom. Why don't we just redo the analysis and just do it this way? X equals mu plus alpha plus beta plus epsilon. Now the variance, this variance better be bloody small because it's all going here. It's all going to epsilon. You can do that. It's rare when people do that. That's a theoretical question you can ask, but practically people don't do that. Because taking that variance out makes you happy. So let's just take it out and just say it's not a significant amount. But you can do that. But you wouldn't use a Latin square in that case. Latin square is under a very specific set of circumstances. When you have an equal number of an equal number of levels of rows, columns, and independent variable. And remember, it's just one subject in each of those levels.